With the understanding of spatial thinking, spatial analysis, now we are ready to look into details on geographical data. Geographic data normally as the representation of any reality. So let's look at what are the realities geographic data are representing. You are likely to encounter three kinds of geographical data. One kind of data basically refer mostly to the geographic feature, like lakes and rivers and cities, etc. And they usually carry information about location and shapes of those features, and they commonly represent as either points and lines and polygons. Polygons refer to those larger features have areas, have boundaries. Okay? And the other kind of data basically don't have the shapes and location, but they usually are descriptions of geographic feature in terms of other attributes. For example, population census data are commonly referred to an ID of a geographic feature, but they mostly describe survey of household income, ages, and etc. So those data can be associated with map data and later on be used for analysis. Okay. The other kind of data that's increasingly available in high resolution are image data. Most of them from satellite image. There's also regular surveillance of localities through aerial photos, and we have much kind of sophisticated photogrammetry technology there that collect those data. So these are all available, and they can all be inputted to geographic information system. Although the phenomena on the Earth's surface can be infinitely complex, can manage to represent them digitally using only three kinds of geographical features. So a feature can be either a point, a line, or a polygon. Points are like a business location, bus stops, and quiet instance. Usually they refer to those small features that don't have enough the size to be an area. Right? And linear feature, they tend to have certain size in the length, but their width is not large enough to become an area. Okay? And area feature usually is significantly sized so that we have to recognize the boundary and inside and outside. Okay? For example, townships and parcels. However, when we try to represent features, those kind of representation in many cases depend on the scale of the problem. Okay, for example, cities can be considered as a big polygon when we really look at the local activity. However, if we look at the whole world, cities are often represented as points. So there can be multiple representations. Another kind of data is commonly available is aggregated or summarized by areas. So data doesn't represent individual features, but they represent a number that is summarized from the individual features. For example, the map on the left shows the business location, and each of the dots actually represent one business location, and these are the individual features. On the other hand, the map on the right shows the summary or count of the number of business on each zip code area. In this case, we no longer know the location of the business, but we only know their aggregated property. GIS organizes geographic data very cleverly in terms of layers and themes. So in the map, you basically see that each of the theme contain the same kind of feature. For example, cities. Okay, all the cities form into one theme. Similarly, we can organize all the streams and rivers into one theme because they are all linear feature, and we can describe them in a uniform way. In the same principle, we can can organize all the countries into the same theme because they all showing the area or polygon feature have different sizes. So in this case, countries are defined as a polygon and their attributes are similar. Okay, so we can represent them in uniform way. Lakes are also represented as aerial feature, and each lake is represented as a polygon. Unlike other themes, the ocean is represented as a raster theme, which means every location, every value, and is represented as pixels or cells, and each cells are considered a uniform value. So raster data is very popular in representing images. The world map you normally see is actually broken up into 5 different themes, and we are free to combine in different order and symbolize each of the themes in different way. So we can have basically infinite number of methods to see the world. If we put all these themes we have seen as map layer and overlay on top of each other, we can make a map with very rich content. For example, this particular map actually shows all the 5 themes together. Okay, if you like, you can hold over the table of contents on each of the map layer, and you can see the correspondence of the themes to the names of the theme, and then how they combine. This shows the power of digital representation and theme-based, layer-based structure of geographical data. In summary, digital representation of the geographical data present the complex of phenomena over the Earth's surface is basically unlimited. The most widely used data model for geographical data is called a vector model. So in this model, all the features are represented as shapes, and each shape could be one of the 3 types: points, lines, or areas. On the slides, you see that points represented coordinates of x, y's. Okay, and the lines, we can represent them as a series of points connected from one to another. And polygon we can think of as a series of points where the starting and ending points actually is the same. They form a loop. So in this case, based on these 3 kind of feature, we can represent infinite number of phenomena. The vector model of data not only represent the geographical attributes, spatial attributes in terms of shapes, but also have a component that describe the non-geographical, non-spatial attributes. For example, each feature may carry a name, maybe a class, or describe a city. We could have population number attached to each city, and the city could belong to a certain state. So this kind of attributes we call it non-spatial attributes, and they are described in a tabular form, and they are linked to the geographical, to the description, and through a unique ID. So by doing this, we can connect, we can link spatial and non-spatial data through a common ID. Vector model assume there's a way to represent the location, pinpoint to the location by, so in geographic space, usually we have to define a geographic coordinate system so that each of the place have a representation in terms of x, y's. Okay. In this case, we will have divide the Earth's surface into different granularity of grid and define origin position in relation to the origin. Okay. For example, the country layer in this map is represented in a vector model, and it has shape representation of each country, and also describe each country by its name and other attributes. In this case, we have shown both the attributes table and the spatial representation in terms of maps. Okay, so looking at the attributes table, there's one column called shape, and it doesn't really have a value, but it shows the shape is a type of polygon. Okay, inside that attributes, basically there's a complex spatial data structure. It represents maybe one or more closed polygon. Okay. In this case, we have highlighted a country, China, by selecting the rows in the table that represent China. In the same time, you will see that the map also highlighted the shape of China, because in GIS both the spatial and non-spatial attributes are linked through their ID. The digital representation in terms of coordinate system basically only represents something as flat. Okay. However, if you look at the Earth's surface, it's not a flat, it's a ball-like thing. And one of the challenges is how can we project the Earth's surface to a flat surface so we can define the coordinates. Okay. The way we project have many alternatives. Sometimes we use a cylinder, sometimes we use cones, sometimes using other shapes. So these are choice of projection, we call it map projection, are all for the convenience of representing locality. Also, there's have different implications in terms of distortion of this Earth surface. Whether we will want to maintain equal area or equal angle is a major choice. Okay, so map projection itself is a separate study topic, but we're not going to go into that too much. In this case, what we try to emphasize is that all the maps that we want to compose into some products must be in the same coordinate system. Okay. Well, the current GIS systems are very much capable of manipulating coordinate system automatically on behalf of human. So many cases, even the coordinate system are not the same. We may use a geographic information system to reproject them. Okay, that's something that normally if we have to consider as one step of geographical processing. So we have talked about geographic information system for many times, but what exactly geographic information system is about?